Okay, let's finish off 3.6. Pretty straightforward from this point on. Okay, we'll do I'll grab both these. We finished number 8. And let's have a look. The polynomial, which is missing k, and k is just a number. A lot of students get freaked by seeing suddenly these missing values. All of math, especially from grade 11 onwards, is about solving for missing numbers with tools you've learned. So obviously we're in a synthetic division chapter, so you're going to use synthetic division and just leave k as it is. Don't freak out. Just say to yourself, what chapter is this? What am I supposed to do? And we're given 2 bits of information here. We're given that not only is that the formula on the left, but it has a known factor. Now, the secret is 2x minus 1 is not a clean number. However, we are told that it is a factor, which means it will definitely go into this mysterious polynomial, and by the end of it, we're going to know what k is just from knowing that this works out. And the secret is the remainder will have to be 0. Okay? So they want us to, what do they want us to do? Determine the value of k. That's it, that's all. Let's try it with synthetic division. First of all, what's the root of this? The root of this is 1 over 2. So it's 1 over 2. If you don't know how to solve those by now, you need to go brush up on what roots are and what factors are. Okay. Next, we're going to try synthetic division. Just remember that at the end of it, we have to divide all the numbers we have at the bottom here by 2. Why by 2? Because while the root is a half, this 2, when it multiplies in, affects all the numbers that we come up with. If we don't divide it by 2, what we're going to end up with is 24x cubed plus double whatever this is, minus 2x minus 12. We're going to end up with double our values that we want. Okay, let's start. We're going to start by lowering the 12. Then we multiply by half, we get 6. Now here's the secret. And remember that we're only dealing in synthetic division, we're just dealing with the coefficients. So get rid of all these x's, make your life easier. And this one here is minus 1. And there's all the coefficients. Now what do we do in synthetic division? We simply add them, right? So why not just keep it together as an addition? Boom. Next, we multiply half times this, right? Okay. So we end up being a half k plus 3. Right? All in brackets if you want. Half k plus 3 is what happens when I distribute this half through. If I add this, the only thing I can add are the numbers. So what's 3 plus minus 1? It's plus 2. So that means down here, I get a half k plus 2. Then I have to multiply by a half again, right? I have to multiply this by a half again. And I get, what's a half times a half k? A quarter k. You only just multiply the fraction in front. What's a half times 2? It's plus 1. Now let's add this. This is the secret right here. If I add this, this is the remainder. We're told this is definitely a factor. Therefore, this answer is going to come out as 0. But I can also add these numbers. What's minus 6 plus 1? Minus 5. So I'm left with this, a quarter k minus 5, because that's what minus 6 plus 1 is, must come out to equal to 0. Right? Now I'm going to just check all my math. Half this is 6. Add them, 6 plus k. Half that is half k plus 3. Subtract 1, so plus 2. Multiply by half, I get a quarter k plus 1. When I add it, I get minus 5. So this is right. Now I'm just going to solve for k. A quarter k must be equal to 5. How do you get rid of a quarter? If I have a quarter in front of a k, multiplying a k, how do I get rid of that quarter? I have to multiply by its reciprocal. That's why I like to say multiply by the reciprocal. And I must do it on both sides. So these will cancel, and I'm left with k is equal to 4 times 5, 20. So it's clear that k is equal to 20, but here's the thing. We want to verify this and make sure that if k said 20 there, that we will indeed get 0. So now we're going to put a 20 up here just to make sure that it all works out. And if it all doesn't work out, that 20 might actually be a 10 because you have to remember divided by 2. But I suspect the 20 is going to work out. So this means 12 comes down. Half times 12 is 6. 20 plus 6 is 26. Half times the 26 is 13. 13 plus 11 minus 1 is 12. Half of 12 is positive 6, and when I add those are 0. Which means, in this equation right here, that is 20. So you can just stop there because that's all they wanted to know. Some books will then say, what are the remaining factors? For instance, you'd have to figure this out, which would be 6, 13x plus 6. And you'd have to find something that adds up to 36. Sorry, it multiplies out to 36, but adds up to 3. So it can get, you'd probably have to use the quadratic function, but they don't. They just want to know k, so we just say therefore k is equal to 20, and we're done. Easier than it looked. And we're going to go on to the next ones. The next ones are all very similar. Some of them are more theoretical. Some of them are not, but they're all sort of the same puzzle. In this case, they give us something where we're missing an a and a b. Instead of a number in front, we're given a and b. So how many variables we're missing when we're missing a and b? We're missing 2 variables, right? We're missing 2 variables, a and b, which means we have to come up with 2 equations. Well, fortunately, they tell us 2 things. That when x minus 1 is a factor, in other words, when 1 is a root, the remainder is 10. So then we know that if we put in 1 into a root at the end, it should leave a 10, which is the same thing. Whatever equation we come up to should equal to 10. And then the second thing they tell us is that when 2 is a root, x minus 2 is a factor, plus 2 is a root, the remainder is 51. So again, whatever equation we come up with should equal to 51. So let's try it out. Let's just go step by step and start with the easiest one, which I would say is the remainder of 10. And they're saying that when 1 is a root, we're going to get 10 as a remainder. So what are the coefficients in front of this? I got a. Let me just make this a little bit bigger. I got minus 1. I've got 2. And I've got b. And no matter what, my remainder should be 10. And you just do synthetic division the same you would for any synthetic division. So I bring the a down. I bring the a down. What's a times 1? A. What's minus 1 plus a? Well, it's the same as a plus minus 1, which is a minus 1. When I multiply that by 1 over here, I get a minus 1. What's 2 plus a minus 1? Well, it's the same as 2 plus a minus 1, which becomes a plus 1. If you can't see how I came up with that, just remember that you're always in synthetic division adding these, where essentially it's 2 plus a minus 1. Here's the only common numbers. So it becomes 1 plus a, but I like putting my a first. Okay? And what's 1 times that? Well, it's a plus 1 this time. What's b plus a plus 1? Well, you can't add anything there. You end up with a plus b plus 1. That's what it all adds up to. And here's the final line. What's 1 times that? Well, it's a plus b plus 1. And now, oh, I missed one there. Sorry. I wasn't supposed to add to b there. 2. Yeah. Let's see if I got it all right. Yeah, I missed one here. Let's try that again. All I did there was slightly screw that up. Oh, no, I didn't, because I brought a down to begin with. All right. So I've got a minus 1 is a coefficient. I got a plus 1 here. When I multiply by 1, I get a plus 1, and I end up with this. And remember, this whole thing is what I ended up with, but I was also supposed to end up with what number? 10. So that means this whole thing here is supposed to be equal to 10, because that was what they told me the remainder would be. Now, I'm just going to make sure I did the math correctly. A minus 1, 1 times that, a minus 1, add that, a plus 1, 1 times that, a plus 1. So I get a plus b plus 1 should be equal to the remainder, which was 10. So if I solve for this, I get a plus b is equal to 9. If I solve it further, I'm going to discover that, let's say, b is equal to 9 minus a. And that's what I want. I want an expression of b that includes a with b on one side. Now I'm going to do this all again. But this time, I've been told that when the root is 2, right here, the remainder is going to be 51. And when I put down the coefficients, I get a. Again, I get minus 1. I get plus 2. And I get b. So I start by bringing the a down. When I multiply by 2, I get 2a. When I add 2a to minus 1, I get 2a minus 1. When I multiply that by 2, I get 4a minus 2. When I add 2 to that, the 2's cancel out. I get 4a. When I multiply that, I get 8a. So that means when I add 8a and b, 8a plus b is equal to 51. Now, I might have gotten the math wrong, but we'll see. Which means I have two equations now. Here's my one equation, that b is equal to this. And here's my another equation, that b, a plus b is equal to that. But whenever you have two equations where you know they're equal, I'm going to do that again. You're allowed to replace b by an equation that you know also equals b. Well, we know here that b is equal to 9 plus a. So that's the equation I'll beat it to, reduce it to. So I got 8a minus a is equal to 9. So that comes to 7a is equal to 42, right? Which means that a, when I divide 42 by a, I get 6. If a is 6, and I come back to here, b is equal to 9 minus a, I get that b is equal to 9 minus 6. Therefore, b is equal to 3. Now I have my three terms. You should go, in a test especially, and replace your a, b, c with the 6, with the minus 1, with the 2, and b is supposed to be 3, and go back and see if those roots work. So you start with your first root, which was 1, and we're supposed to end up with a remainder of 10. So I bring my 6 down, multiply by 1, 6, get a 5, multiply by 5, 7. 7, multiplied by 1 is 7, and when I add 7 and 3, I get 10. So far, so good. Now we go back and we try the root of 2, which was the second problem. And the root of 2, we're supposed to end up with a remainder of 51. So we start with the 6, times 2 is 12, added together is 11, times 2 is 22, added together is 24, times 2 is 48, 48 plus 3, 51. So we can see that these are indeed the answers. B is equal to 3, A is equal to 6. And we didn't even have to check the answers because we were able to verify it by doing it again. Okay. Determine a general rule to help decide if x minus a or x plus a are factors of these two things. Let's start with the first one. And let's just start with practical items. Okay? Pretend it was x to the 2 minus a to the 2. That's where n would be equal to 2. It's clear that we have x plus 1 and x minus 1. Right? It's also clear that when that's just 1, there's only x minus 1. So I'm going to, before I go on, I'm going to suspect that when it's even for this one, for subtraction, they're both going to be a factor, and when it's odd, just x minus a is going to be a factor. That's just a guess. Let's start with x minus 1 to the power 3. Well, we know from our cubics, right, oh, that's not like that, sorry. From our difference of cubes, that is indeed x minus 1 is a factor, but x plus 1 is not a factor. It ends up being, I believe, x squared, was it minus 2xa plus a squared? Look up your difference of cubes, but my point is, one of the other factors is not x plus a. And if we continue on to x to the 4, we discover that x to the 4 is no different than the difference of cubes. X to the 4 minus a to the 4 is the same as the difference of cubes x squared minus a squared times x squared plus a squared. And we quickly see the difference of cubes again, x plus a, x minus a. So I will reach the conclusion for this. Here's my general rule for this one. For this one, I'm going to suggest that x minus a and x plus a are factors. Are factors when n is even. Then I'm going to say when n is an odd number, only x minus a is a factor. And that just was done with a simple checkup, because when we hit x to the 3 minus a to the 3, we discovered that only x minus a was a factor. And if you look up your difference of cubes, the other factor is not x plus a. Then I'm going to go out on a limb and say for x plus a to the n, we're only going to get x plus a to as a factor. But let's try a practical analysis. When it's just x to the 1 plus a to the 1, we discover that only this is a factor. When it's x to the 2 plus a to the 2, that's not a factorable at all. It's a plus. We're missing the plus 2xa in the middle. It's not factorable. Then when we come to x plus x to the cube plus a to the cube, that's a difference of cubes, and I know that it's x plus a is one of the factors, and then the other factor is not x minus a. You'd have to look it up, but it's a complicated one. And it is not x plus a either, so this is only true when it's cubed. And then back to when it's to the power of 4, we can see that it's not factorable at all. So now I'm going to jump out on a limb and say that for this, I'm going to say x plus a is a factor when n is odd. When n is even, neither is a factor. So we're going to just look that up now. I have the answers here. It's number 11. So we're going to do that and just copy it and see if I got it right. Okay, they're saying, oh, and there's the answer to A and B right there. They're saying x to the minus n, when n is even, they're both factors, which is what we said right here. And if n is odd, only x minus a is a factor, which is what we said right here. For x to the n plus a to the n, if n is even, neither is a factor, which is what we said here. And if n is odd, only x plus a is a factor, which is what we said right there. Good. So we're going to continue. Go on to 12, which is the same thing. 12 is saying the function that's missing a and b has 3 factors. 2 of these factors are given, which means the remainder will be 0. So this is very much like the one we just did. They want the values of a and b, and they want all the factors. So let's just start with what we know. We know the coefficients in front of this are a, minus 1, plus b, and minus 24. And we know also that for a factor, the remainder is going to be 0. So at the very end here, we should come to 0. And they're telling us that 2 of these have x minus 2 and x plus 4, which means the roots are plus 2 and minus 4. So we'll start with the easy one, 2. We'll bring the a down. multiplied by 2, get 2a. We're going to add those together. We get 2a minus 1, very similar. Didn't we do this? Let me make sure I did. No, I didn't do this. This is just a similar one, but now they want the equation. Yeah. 2a minus 1. When I multiply that by 2, I get 4a minus 2. When I add all this is the complicated part, I get 4a minus 2 plus b. When I multiply that by 2, I get 8a minus 4 plus 2b. Now that means when I add minus 24, in other words, when I subtract 24 from this, I should be equal to 0. Which means that this minus 24 should be equal to 0. So we're just going to solve it. We're going to add 24 to this side, and we're going to add 4 to this side, so it's going to be 28. And we're left with 8a plus 2b is equal to 28. Then we're just going to get b on its own side. 2b is equal to 28 minus 8a. We're going to divide 2 on the left side and 2 on the right side. We're left with that. So we have one equation right there. That's one equation. We'll put it aside. And we'll proceed with the same logic with the other root. The other root is minus 4. We know that the remainder is supposed to be equal to 0 again. So we get a. Minus 4 times a is minus 4a. When we add those together, we get minus 4a minus 1. We get 16a plus 4. When we add those together, we get 16a plus 4 plus b. And when we multiply that by 4, minus 4, we get minus, minus 64, minus 16, minus 4b. Now, for this equation, when I add this to that, I'm going to equal 0 again. It's going to be equal to 0. So again, I'm going to put all the numbers on the same side. So 64, negative 64 goes over here to 64, negative 24 goes over here. Oops, I forgot it's minus, oh, I got it. So it's negative 24 goes over there, but also negative 16 goes over there. And that's, sorry, the 64 doesn't go over there. That's supposed to be 64, negative 64a here. So I'll redo it. It's supposed to be negative 64a minus 16 minus 4b minus 24 is equal to 0. So I get minus 64a minus 4b is equal to 40. I can divide everything by 4. Yeah, 4. Minus 16a minus b is equal to 40. You can also do it this way if you want. You can say, okay, put the minus 40 on this side is equal to b. Now you have two equations that equal to b, right? Which means if this is equal to b and this is equal to b, you're allowed to do this. So if I put the minus 4a on this side, actually let's put the minus 16a on that side, and I get minus 4a plus 16a, which is positive 12a. When I put the plus 14 on this side, I get minus 54. Now let me make sure that I didn't do something wrong there. Yeah, you know what? No, that should still have worked out, but let's keep it. Let me check my math one more time. Minus 4a, when I add that minus 4a minus 1, I get plus 16a plus 4, yep. When I add that, I get the same thing plus b. When I multiply by minus 4, I get minus 64 minus 16, yep. Minus 4b minus 24 is equal to 0. Okay. put it all on the same side. Let's put 64a plus 4b on the other side is equal to minus 40. There we go. I think I just might have forgotten to divide by 4 there. And now, yeah, that's what I did. So now if I divide by 4, I get this. Now you see the b there? I can replace the b with my equation on the left side. What's 16a minus 4a? 12a. What happens when I bring the 54 to the other side? Great. Now, my problem is a does not look like it's an even number. So maybe I should not have divided. Let's keep it like this. And let's do times 14 minus. Let's replace b right here. And I think actually I did do correctly when I added together, but I'm left with this 64a plus 56, and that's, sorry, that's minus 14 minus 4a. When I multiply that, I get minus 16a is equal to minus 40. I think it still works. So 48a is equal to minus 96. Okay, there we go. Because the equations were being equated, I don't think I could divide out the 4 like that. Although I think it should still have worked out. So a is equal to minus 2. So there we go. Now that I have a, I can go back here and say b is equal to 14 minus 4 times minus 4 times minus 2, which is plus 8. So b is equal to 22. If I go back and I say, okay, my a is minus 2, and my b is 22, I should get the same things. I should have, both these should be roots. And so if I just bring down the exponents, I get minus 2. Sorry, if I bring down the exponents here, minus 2, minus 1, 22, minus 24, and I just do it, I should get a remainder of 0. I do in this one. I get plus 24 here, which cancels out the minus 24. So that worked. And if I do it with the 2 here, I should also get a remainder of 0. Oh, and actually I should just continue here because they want the other factor. Let's see if it'll let me get there, if I can bring it all. No, it won't. I'll start with the 2. It doesn't matter. I'll just do it again with the 2. It doesn't matter. So minus 2. Minus 4. Minus 5. Minus 10. When I add those together, I get 12. When I multiply those together, I get 24, and they cancel out, which means I'm left with these new ones as coefficients. And I can go on with my minus 4, so it was my mistake erasing them to figure it out. And I just start with the minus 2 here. When I multiply by minus 4, I get 8. When I add them, I get 3. And when I multiply it, I get minus 12, which means my last factor here is minus 2x plus 3, which is the same as, I don't think I'm supposed to have a minus 2x. Oh, yeah. Yeah, you can. That makes sense. And actually, I'm going to factor out the 2x and put this, and there's probably a minus 1 in front. But if I'm just going to leave it as is, it's going to be this, which means minus 2x is equal to minus 3, which means x is equal to 3 over 2, for that to be the last root. If instead I wanted to go back to this one and just say minus 2x squared minus 5 plus 12 you would factor out the 2, the minus y rather, but you can't in this case because one of them has to be in there. Let's see what it says instead of going to the trouble of doing a factor here. No, we got it right. There it is there. It's just weird for me to have a minus in front of the x. You'd normally instead have a minus 1 in front and have 2x minus 3 as the factor, because you usually want a positive coefficient here, and so that would be an a value in front. But that's okay. Either way is correct. This is what they're looking for algebraically. Let's move on to 13. Okay, they're doing the same thing, except they're getting into a riddle. They're saying the remainder from using this root is twice the remainder of this one. So it's just an equation again. I'll do it, but this is stupid. You'd never really do it. Just focus on the factors they're giving us. So what are the coefficients here? It's 1, 4, k, and minus 2. And they're saying, start with the first root here. I'm going to start with this root here. Positive 2. So if I do that with positive 2, I bring down the 1. I get 2. Add it, 6. 12. So I get k plus 12, or 12 plus k. When I multiply it by 2, I get 2k plus 24. And when I add it to minus 4, I get a final result of 2k minus 20. Now that doesn't matter right now, or plus 20 rather. That doesn't matter right now. Just keep that in mind as a result. 2k plus 20 is the remainder of this one. Now we're going to go back. We're going to use the other one here, which is minus 2. And we're going to do the same thing again. Bring down the 1. When I multiply that by 2, I get minus 2, I get minus 2. When I add that together, I get 2. When I multiply, I get minus 4. When I add that together, I get k minus 4. When I multiply that by minus 2, I get minus 2k plus 4. Then I have to subtract 4. So I get minus 2k. Is the final, let me make sure. Oh, no, it's not. Minus 2 times k is minus 2k plus 8. And when I add those together, I get minus 2k plus 4. There we go. So that means that's my second value. Now read this. This remainder here, which is that, is twice the remainder of this. Determine the value of k. Okay. So rewritten, this is equal to 2 times this remainder. Okay, expand the right side. Okay. Oops. That's not the proper expansion. Write the left side again. Okay. Bring the k to this side and the plus 4 to that side. I get minus 36 on the left side is equal to 6k. When I divide out the 6, I get k is equal to minus 6. So you could verify it, put the minus 6 in here, and when you take the remainder, whatever remainder you get, so let's just do it. If k is minus 6, then if k is minus 6 here, we get minus 12 plus 20, which is 8, and which means that this will come out as 16. If minus 6 is here, we get plus 12 plus 4, 16, which is 2 times 8. So that means that k over here is indeed minus 6. It's the same thing. They're just asking you to stretch your mind muscles. Okay, let's see. Okay, right there, minus 6. No, that's a different one. Yeah, no, that's it, minus 6. Okay, we're going to go on to the next one. Almost done. Okay, this is almost the same thing. We already did this. Show that for sure x minus a is a factor of that. What's the second one? X to the 4 minus x minus a to the 4. Well, that's a difference of 2 squares. It'll be x squared plus a squared. And x squared minus a squared. Like this. Well, that first one can't be factored, so it's just going to stay the same. But the second one is a difference of squares again. And it's x plus 1 and x minus a. X plus a minus x minus a. So it doesn't matter if there's an a in there. These rules still work. You just treat a like a number. And right there we've proven that x minus a is indeed a factor of this, just by using simple difference of squares. What I think they wanted us to do, though, is use synthetic division. So what is the root of x minus a? It's positive a. What are the coefficients in front of here? Well, keep in mind that a is a number, so it's 1 in front of the x to the 4. It's 0 in front of x to the 3. It's 0 in front of x to the 2. It's 0 in front of x to the 1. And then it's the number minus a to the power of 4. Now, personally, I like our solution. So that's some number to the power of 4. However, it works still. So or at least I hope it works. So we're just proving that this is a factor of that. All right. Bring the 1 down times the a. Add the a, I get a. When I multiply that by a, I get a squared. Bring it down, I get a squared. Multiply that by a, I get a cubed. Add it to the 0, I get a cubed. Multiply that by a, I get positive. Oh, by the way, positive a to the 4. And by the way, I shouldn't have put brackets here. I should have put it like this, because what they're saying up here is they're saying I'm going to put a to the 4 and then multiply by minus 1. And here's a to the 4 and positive. It's clear they cancel out, and 0, which means the remainder is 0, which means a is a factor, which means x minus a is a factor of this using synthetic division. And I probably should have used synthetic division for those other ones to prove, since we're in the synthetic division. Explain why the factor theorem works. The factor theorem just is about the remainder. Why it's essentially saying why x minus 1. Why is it that you put plus 1 into the equation and it comes out 0? And that this proves that this is indeed a factor when I'm putting the root into the equation. And that's quite simple. If x minus 1 is a factor, we've always said that it's on the x-intercept line. If it's on the x-intercept line, y is 0. If y is 0, it means that when I would plug in plus 1 into this equation, the whole thing would come out as 0. Therefore, a root, when plugged into the equation, will produce a remainder of 0 because it's always on the x-intercept. Now, I don't know how they phrased it, if they phrased it a bit differently or not at all. It'd be interesting to see. Oh, look at that. In their thing, they did difference of squares, too. When we're in factor theorem, they missed their own point. For their proof of 15, they did it weirdly. They're saying that They're saying that they're taking an example of any factor, and they're saying if I plug a into this, it's clear that it becomes 0. Fair enough. Mind you, they rigged their own game on that one. Use factor theorem to prove that this is a factor of that. And the secret here is you might say, well, I can't use factor theorem for this, except that you're going to notice that the factors of this up here are x minus 2 and x plus 1, which means if minus 1 is a synthetic division and plus 2 goes in synthetic division, then this is definitely a factor. So you have to sort of prove it twice. So we're proving it for positive 2 and for minus 1. So you take the coefficients in front of this polynomial, and you get that. And then you work with each one individually. And they should both work into the original polynomial if they are factors. Add it, multiply by 2, add it, multiply it by 2, add it, multiply it by 2. Do they cancel out? Yes, they do. Okay, that means this is indeed a factor. Let's do it again, but for negative 1. You could also factor that, your x squared minus 4x minus 5, and you discover that it's x minus 5, x plus 1, and you've instantly proven this, and you've also discovered the other factor. But let's just use synthetic division. You could also use synthetic division on these, because negative 1 should still go into those, but it doesn't matter. Negative 1 should go into either polynomial if it's a factor. So you start with negative 1, you bring down the 1, you multiply by negative 1, you bring it down by adding them, you multiply by negative 1, you bring it down by, oh, I made a small error somewhere. You start with 1, then you do negative 1, you add them together, you multiply it by 1, that's my small error right there, 10, multiply that by negative 1, boom, right there. And it would have worked if I'd factored 1 into this polynomial or into this polynomial, into the other polynomial. I can also factor plus 2 into this polynomial. It'll all work out. Use factor theorem. Oh, this is the last one. Oh, I don't know if I can prove this. Hang on. Ugh. Yeah, I don't know if I can prove this. I mean, so it's got to be factored into each of those. And I suppose you could go crazy and expand it. Or you could treat, what could you treat? That's like a number plus a. Ooh. I think that's brutal. You're essentially saying, will minus a be a factor? Huh. Yeah, I don't think I can do this one. You might want to ask your professor. We'll see what the answer says. Maybe we'll get some hints from that. Oh, okay. Fair enough. It's saying that if this indeed is a factor, if I put minus a in for everywhere I see x, it should come out as 0. So if I put minus a here, because this is what the root is, right? Minus a, which means if I plug it into the equation, it should come out as 0. So minus a plus a, that's indeed 0. Minus a plus c is something we can't figure out yet, except that we're also adding a minus c to the 5, and theoretically anything, this is c minus a over here, and this is a minus c over here. Theoretically, 7 minus 2 to the, let's do an easy one, 4 minus 2 to the power of 5 should be the opposite of 2 minus 4 to the power of 5. So here you get 2 to the power of 5, and here you get negative 2 to the power of 5. So it's quite clear when I use numbers. So because these are switched numbers, it's essentially saying a negative whatever this is added to a positive whatever this is will be 0. And you have to fiddle a bit with the numbers. You could also expand this and expand all that, and then you will see the common terms will cancel each other out. But yeah, that was silly of me. That was actually a pretty easy one. There you go. That's good for now. That's the end of 3.6. You can see it's just mostly slogging through the calculations.